Let's see, is my streaming working? It appears to be working. That's good. So it's right about 4 o'clock. I'm assuming everyone on the YouTube audience can see this and they can hear me. So I guess we should get started. So welcome everybody to Mathematics Society's MATH3711/5706 revision seminar. My name is James. I will be taking the first half of today's session. So I will be reviewing all of the stuff from basic groups all the way up to homomorphisms and the isomorphism theorems. And then after this, Bruce will take over to talk about group actions and the rest of the stuff before on Thursday, Gerald starts and to talk about fields and rings. So my part of the revision seminar, in a sec, let me drink a bit of water. Okay. So as I said, I'm going to be covering these first two things here. So introduction to group theory and group homomorphisms. And then Bruce is going to take these two, and then Gerald will do the other two on Thursday. So introduction to group theory should be quite light, because I imagine that we've probably come across the concept of a group and the related notions quite a few times now. So I won't go too much into detail with this, but in case you've forgotten the axioms of a group, so a group is just a set G with some multiplication map such that it's associative, you have an identity element, and each element has an inverse. So it's a nice set with a multiplication map with these three properties. Obviously, you would have seen that writing out this star every time is a bit inconvenient, so oftentimes we'll just drop that and just write GH like this, and we can do repeated multiplication in this way just using powers, kind of just the way that you would have done for numbers. So this should all be quite familiar. So some common sense properties of groups are that the identity element is always unique. The inverse element is always unique for each element as well. When you invert something, you just take the reverse ordered product of each element's inverses, and you have the similar properties that you would have for real numbers, where if you raise something to a sum power, it's just the product of each individual power, and so on and so forth. So these are all very basic and nice properties that we would have seen before, but they're true in general for groups. To talk about the size of elements and groups, we can talk about order. So the order of an element is just how many times you need to multiply it in the group to get back to the identity. So how many things you have to multiply together to get back to 1, which is what we usually write for the identity. And if we've got that in a finite number n, then we say that the order of G is just n. And if no such integer exists, i.e. you multiply this as many times as you like and you never get back to the identity, then the element has infinite order. And the order of a group is a little bit simpler. It's literally just the cardinality of the set, because groups are ultimately just sets with a fancy operation defined on it. And clearly, if the set has finitely many elements, we should probably call it a finite group. Within groups, you can obviously have smaller groups, so you might have a subset that actually is a group in its own right with the same multiplication. That's exactly what a subgroup is. So it's a non-empty subset of a group G which satisfies all of the group axioms, and if that happens, then we call it a subgroup. Proving that it's a group from scratch is a little bit annoying, so we do have this nice subgroup test, which you might have seen, which is essentially just saying that it's a subgroup if it's, well, non-empty subset, obviously, and closed under multiplication, so you multiply two elements in your subset, you stay in your subset, and also if you take an inverse, you also stay in your subset. If you have those two properties, then it's a subgroup. And this is often the way that you want to go about proving something's a subgroup instead of actually proving from scratch that it's a group. So let us take a look at a quick example just to show off some of the questions that you might see really on the basic material. So I guess a quick word about how I'm going to do these questions for my bit of the talk. If you've had a look at the exams, then you'll notice that a lot of the content is on the stuff that would have been after class test 1. So really the questions that you get on this material early on in the exam isn't too difficult, but what you might occasionally see is a harder example, which might take a bit of thought. So I've aimed to choose questions that kind of fall more into that category than nice and easy ones. So this question here is essentially saying that if you've got some group and there is some element in it such that if you just remove that, so you consider the subset with just one element removed, if that is actually a subgroup, then the original group you started with just had to have two elements. So I guess another way of saying this, or another way of proving this, is that if the set here has two elements, then this thing after we remove one element from it should just have one element. And if you remember back to, I guess, properties of a group, you can't have an empty group. So the smallest group you can have is just the one that contains the identity. And obviously every group has to have an identity element. That was one of the axioms. So I guess if we're saying that the size of G, or the order of G, is 2, then this thing here, H, just has to contain the identity. So I guess one strategy, one way that we might take this, is that I might start with something, suppose that it's in H, so just take some element in H, and eventually just prove that it's the identity. So at the end of some chain of reasoning, I should be able to prove that H is actually just 1. Now, it's not immediately clear how I could do that. I guess one way I could do this, or one thing I can look at, is I basically just have definitions at this point. So there's two facts I know. I know that H is a subgroup, so I have SG1 and SG2 here. I can use those. But I also know that G is the only element not in the group. So one interesting way I could go about proving that if this thing here is not just the identity, then I've got some other element in my group, is I could just prove that the existence of some other element aside from H actually implies that G is in this set here, H. So that is an interesting way to go about this. Maybe it's not completely obvious, but again, if you're in an exam like this and you see this kind of question, then you really only have to use definitions because you don't have much else, right? So let's go for that. How would I come up with such an example? So ultimately my goal is to show that this thing G here is in this set H if some other element is in this set. So I need to pick that other element first. Taking inverses is probably not going to be too helpful, but maybe SG1 is nice, because maybe I could try and get some element in H that kind of involves G somehow, so maybe it's a product involving G, and then I could use SG1, i.e. the fact that if I multiply two things in H, then I get another element of H, to take that product, make it simplify down into G, and then I've got my contradiction, right? So maybe one element, if you do a bit of thinking, could be GH inverse. Because if I suppose that GH inverse is in H, then I could multiply on the right by H here, this thing that I know is definitely in H, and I would just get G, right? Because GH inverse H is just G. So it obviously has to be the case that this can't be in this set. And the reason for that is if you just use SG1, well, you get exactly what I said earlier, right? So this would lead to the fact that G is in H, but that's clearly false, because G is the only element that we've excluded. So if that's the case, then it means I found an element that's not in H, right? So it's not in this subgroup H. But there's only one element that isn't in this subgroup, G, right? There's only one element in H that's not in G. So it must be the case that this thing, which I've just shown is actually not in my subgroup, this has to be G. So this just implies that GH inverse is G, and if you do a bit of rearrangement, you'll see that that actually ends up implying that H is just the identity. So just a bit of left and right multiplication will get you there. So we've done, as we originally set out to do, we've taken some arbitrary H and H, and we've proven via some chain of reasoning that H is actually just the identity, right? Which is exactly what we would expect, because if this thing here was true, then H is just 1, so it's just a one element set, so it obviously just has to be the identity. And that's enough to finish off the proof. So this is a nice small one, but it takes a bit of thought, particularly this choice of element here, GH inverse. That was probably where most of the proof is. But this kind of thing might be a nice example that they might throw in the exam to test how much you really know this. So going back to some stuff that we're probably quite familiar with, one important group that you look at early on is, I guess, sets of permutations, right? So a permutation is essentially just a bijection from a set to itself. So if I look at, let's just say, any set of n things, so maybe the numbers 1 through to n, and I look at all the permutations I can define on that, I get something called the symmetric group. So this symmetric group here is just going to be all of the bijections from S to itself, and the multiplication is just function composition. So when you multiply permutations, you essentially take their composition. And obviously it's pretty apparent that because we're talking about permutations, this is a finite group. It has n factorial elements, because that's how many permutations there are. We can represent things in this symmetric group a couple of ways. So we can do two-line notation, which is basically just like write out what element goes to what thing. Or you could write in cycles. You might have to do a product of these, but if you can look at all of the cycles in the permutation, you can write it as a product of these kinds of things. And what you'll end up with is essentially an equivalent representation. And these cycles here, k things, you might expect to have order k, that's exactly right. So we call them k cycles. Special kinds of cycles, so you can have a transposition if it basically just deals with two elements, i.e. it's basically just transposing them, i.e. swapping them. Basic if you're swapping adjacent things, so if you're swapping I and I plus 1, it's a basic transposition. And in the same way that we've got this idea of disjoint sets, we have disjoint cycles, and they work exactly the way that you would have seen. So, useful facts about cycles are that if you're working with disjoint cycles, they obviously commute. You can decompose any k cycle into a product of transpositions in a pretty nice way. Basically just take pairs and turn them into transpositions. And you can write any permutation in, I guess, 3 different ways. You can either write it as a product of disjoint cycles, as a product of transpositions, or if you'd like those transpositions to be basic, you can also do that. You can look at the sign of a permutation, which I guess is just some sort of measure of whether the number of items it swaps from being less than and bigger than, I guess, is an even or an odd quantity. So if you take a pair of numbers x and y, you throw them through your permutation, and they're initially less than each other, so you had x less than y, but after you've permuted them, it's the other way around, then you can call that an inversion. And an even permutation is just going to be one where you have an even number of such occurrences of these swaps. And an odd permutation, I guess you can kind of see where that goes. It's basically you've got an odd number of these. And once you've got that, you can say that the sign of the permutation is 1 if it's even, and -1 if it's odd. So pretty natural. But I guess there's another way that you can think about the sign. I guess 2 facts that go into this are that the sign is actually multiplicative, in that the sign of a product or composition, I guess, is just going to be the product of the signs. The sign of any transposition is going to be -1. And you can write, obviously, any permutation as a product of transpositions. So using this first one here, you can essentially just say that the sign is basically -1 to however many transpositions go into its decomposition like that. So this is probably the one that you want to work with, provided that you can write sigma, I guess, in this transposition product quite easily. Last comment about the symmetric group is that there is a nice subgroup of it. So if you take all of the permutations which are even, then you get the alternating group. So you can prove that this is a subgroup. And that's one nice subgroup that's present here. So moving on, I guess now we can talk about more interesting types of subgroups. So one natural thing you might have seen, or you might think is, well, what if I start with some subset of my group? Maybe it's not necessarily a subgroup in its own right, but I'm interested in finding a subgroup that contains all of these elements. How can I find one? Well, one nice subgroup that has this property, if I take all of the subgroups that contain this set, so all of the subgroups in G which contain S, and I take the intersection of them, you can prove that the intersection of subgroups is again a subgroup. So if you take the intersection of all of these subgroups that contain S, you get what we call the subgroup generated by S. And it turns out that this is actually the smallest subgroup with this subset contained in it. So in terms of the number of elements, this bracket S generated subgroup here is actually going to be the smallest one. You can write it in a different way. So obviously, working out what this set of all subgroups, I should say, that contain S is a little bit tricky. So you might not be able to do that nice and easily. One other way you can talk about this generated subgroup is that it's essentially just the product of all elements in your subset together with their inverses. So I guess the inverses is pretty natural because we want a group ultimately. So we're going to need inverses in there somewhere. So if I take the product of arbitrarily many elements in S and their inverses, I get the same thing. And obviously if I take 0 of these, then I guess notionally we just say that that's just going to be 1. So the empty product is 1. So this is often a nicer way to think about the generated subgroup. A couple things we can say about groups once we can talk about generators is that a group is finitely generated if there is some subset of it, which actually when you generate from that subset you get the whole group back. So if you've got some subset S of G such that when you look at the generated subgroup it's actually G itself, then we say that G is finitely generated and that S is a generating set. And if you have this just for one element, so if this set S here is only one element big, then we call this group cyclic. So this group here is cyclic, and we call G a generator. So it's cyclic because I guess it just contains powers of G. So once you get up to a certain point, you basically loop back to the identity, so you got cycles basically. So cyclic groups are quite important. We'll talk a lot about those in this seminar. Whoops, I don't know what I just did. Where were we? Here we were. Yes, so we'll talk about generated subgroups quite a lot in this seminar. I guess one example is that these finitely generated groups are not finite. You've got the integers as a counterexample of that. They're generated by 1. So another exercise that we could do, another potential exam question, what if we want to prove that the rationals are not cyclic? So this is the additive rational group. So this is just addition as you would know it. You just add two rational numbers together. Turns out that this is a group, not too hard to see that. And we want to prove that it's not cyclic, i.e. it's not generated by some element A on B, right? So if we want to prove that this group here is not actually just a cyclic group, i.e. it doesn't have just a single element as a generator, then I guess where we're headed, or I guess the intuition behind this, is that I want to find some element of the rationals, some rational number, which is not in this set. So if I can't find such an element, then it has to be the case that this is probably at least a superset of Q, right? But in this case, all I'm interested in is looking for something that's in Q, but not in this generated group on the right-hand side. So if I look a little bit more closely of what A on B is, this generator A on B, this, since I'm working with an additive group, is essentially just the integer multiples of A on B, right? Because the product of these is just going to be essentially, you know, A on B plus whatever, right? But the inverse of each element is just the negative, so it's just negative A on B. So essentially, once you take all of the possible products, or I guess in this case, sum of elements, then you'll essentially just get the integer multiples of the fraction A on B, right? So we want to find some element which doesn't have this form. So some element which doesn't have the form NA over B. And I guess one easy one to look at is, what if I was to prove that NA on B is equal to some fraction, then this thing here is no longer an integer. So what if I look for some rational number where if NA on B is equal to that number, this has to not be an integer? Well, I guess the simplest way that we could do that is to just consider A on 2B. So this is certainly a rational number, so it's certainly in Q, but it's not here because I would have to have n is equal to a half. But that's ridiculous because I said that n has to be an integer. So this can't be an integer multiple, so clearly this generated subgroup misses some elements, and so the rationals are not a cyclic group. So that's a nice quick one. Another group which you would have seen in this first bit of the course is the dihedral group. So this is, I guess, the group of symmetries of a regular n-gon for n greater than or equal to 3. So it is a generated subgroup by some rotation and some reflection. It has this form, and when you look at this, obviously as a function group, so all of these things here are basically functions, it's natural to consider that the multiplication should be function composition, and once you take that you get the dihedral group. So you can see here from this representation that it's got 2n elements, order of every rotation, or I guess this rotation here is n, and you know, reflections always have order 2. and the rest of these elements here are also reflections. So I won't go over this slide just because I want to keep this first bit of the seminar under an hour, but I do have a couple of slides included in this first bit that you can read. This is just one about the subgroup structure of the dihedral group, which you may find helpful. So an example of the dihedral group, this is one that I found from a really, really old exam. So this is looking at all dihedral groups as, I guess, matrices. So this is going to be, if we look at the rotation, this is going to look like this. So this is very obviously a rotation matrix about 2 pi over n. And this here is a reflection, some sort of reflection. So if we treat these as, I guess, the isometries that we were talking about or would be talking about in this description here, then I have some sort of matrix group as well. And I'm going to call one of these groups crystallographic if this number here, 4 cosine squared of pi over n, is an integer. So if this thing here is an integer, then the corresponding dihedral group is called crystallographic. I'm not quite sure where that term comes from, but that's just what it says in the exam. So the first part of this question is to find all n for which this dihedral group is crystallographic. And then we want to look at what kind of geometric figures are associated with each of these crystallographic groups. This first part, I'm not really going to go through it because it's just a bunch of equation solving. This is hardly even algebra at this point. I guess the key thing to note is that 4 cosine squared pi over n is only one of these values here, so it only suffices to consider these 5 cases, obviously because the cosine squared of pi over n is between 0 and 1, right? And once you scale that by 4, you essentially look at all of the integers between 0 and 4, which is clearly just 0, 1, 2, 3, 4. And then if you look at only the positive integers n, because I guess we haven't ever really talked about how to define the dihedral group for negative n, if we limit ourselves to just positive n, and you go solve these equations, then you get essentially n equal to 1, 2, 3, 4, and 6 satisfy it. So each of these cases gives you a different value of n. So if we look at the geometric figures associated to each of these objects, well, I guess for 3, 4, and 6 it's pretty obvious because we had the intuition before. It's just the symmetry group of the regular n-gon. So for 3, this is just the an equilateral triangle. For 4, it's just a square, and for 6, it's just a regular hexagon. So these are the regular n-gons for those values of n. But what the heck is d1 and d2? So what are these d1, d2 things that we solved for here? Well, I guess this is one where if you're in an exam, this would mostly be a test of recall, because it's kind of difficult to tell what they should be. Like, they don't really follow the same logic as we had back on this slide. Like, there's no real 1-gon or 2-gon that comes to mind. So I'll just share with you what it is. You might have heard this. D1, if you want to associate it with a geometric object, you can kind of think about it as the symmetry group of a single point, but with a self-loop on that point. So there'll be a picture on the next slide that I'll show you. But we can think of D1 in this way. So it's the symmetry group of a single point with some sort of self-loop. And we can think of D2 as the symmetry group of a pair of points with 2 different edges between them. So note here that I haven't said that D1 is just the symmetry group of a point and D2 is the symmetry group of a straight line, because that's just not true. In this case, the objects end up being a little bit more funky. And in fact, if we look at a textbook from Arton, so if you look at his algebra textbook, he actually gives a nice picture of what these kind of things would look like. So they look a bit funky almost. Like, here's the 1-gon, kind of got a loop, but I guess this would have to be infinitesimally small because we're talking about a reflection and a rotation. So the logic kind of breaks down, basically. So this question here was probably mostly just a test of like how good your memory is, because I don't know how you could come up with this on the spot. So I guess for your information, you now know. If you ever get asked what D1 and D2 are, you know. So moving on, we can talk about special kinds of sets, and this is all leading towards the definition of a quotient group, which we'll talk about shortly. But to get there, we talk about left cosets first. These are essentially just subsets where you take the product of some element with all of the elements of some subgroup. So you pick some subgroup H of G, some element G, and you just consider the product of GH, where H is just any element in H. And then you look at this set, that forms your left coset of H in G. And if you look at the set of all left cosets, then that's written G over H. Now I've talked about left cosets here. You may have seen in the tutorial problems that there's actually right versions of all of these. So you can talk about right cosets, but they turn out to be basically equivalent. So we will basically just work with left cosets as pretty much everyone does. One example that you would have seen is the cosets of the integers. So the cosets of the integers are essentially just going to be remainder classes modulo m, right? So they're going to be sets of numbers which have some remainder r, where r is between 0 and, I guess, up to m minus 1. Not including m, because obviously the remainder of m is just going to be 0, right? So this stems from the fact that if you scale the integers by some other integer m, you actually get a subgroup of the integers back. So if you consider the cosets of this scaled integer group, you get these kind of things, these remainder classes modulo m, and if you put it another way to write this is that you can just write a number with a bar over the top. That's another sort of way that we write these. And one thing to note here that you would have seen is that every single integer in the integers appears in exactly one of these things. So exactly one of these cosets. And that turns out not to be a coincidence. So you can think of cosets as, I guess, equivalence classes of some equivalence relation, the equivalence relation being that two elements are related if they're in the same coset. So obviously this implies that this relation that I've got is an equivalence class, equivalence relation I should say, and these things here, these left cosets, are equivalence classes. So if you know a little bit from discrete math, then you know that these actually partition G, which is to say that there's actually a disjoint union of cosets. So the upshot here is that all of the cosets are actually distinct. So when you're looking at two cosets, one useful fact is that they're either going to be completely different or they're going to be the same. So if you find that there's an element in two cosets which is shared, they have to be the same because they're either equal or not equal at all. So that's one nice little property of this comment here. The index of a subgroup is a notion related to cosets. If you take a subgroup H, it's just going to be the number of left cosets of H and G. Equivalently, you can say that it's just the size of this set G over H. One important theorem you can have when we're talking about index and cosets and all of that is Lagrange's theorem. So this is a relationship between a subgroup's order and its index. So if you start with a finite group, finite being important here, and you look for every subgroup's order is actually going to divide the order of the big group. So every subgroup's order divides the order of the group, and moreover, the number of left cosets of that subgroup, so the index of H and G, is actually just, well, I guess without knowing this theorem, it's basically just the size of this set G over H, but we can actually distribute the size out of this, I guess, quotient thing, kind of like how we would deal with the fractions, even though that's like not really what's going on here at all. But the theorem suggests that even though those two notions are completely unrelated, they actually behave the same way, which is quite nice. So the index of a subgroup is just the size of G over the size of H. So that quotient there is your index. Normal subgroups are a special kind of subgroup. So earlier I mentioned that you could have left and right cosets, and it turns out that you can have, I guess, similar notions of the results for left cosets and right cosets. They're not the same though. So in general, you don't have the same thing. So left cosets, right cosets, they're not the same. When they are, this is actually quite special, and we call this subgroup here N a normal subgroup if all of the left and the right cosets are the same for each G and G, right? And we write it using this, I guess, less than or equal to symbol, except you have a triangle. I'm not quite sure how you say that, but that's the symbol. Another way, I guess the most minimal way that you could talk about what is a normal subgroup, is if you take some element G and some element N in some subgroup, if this conjugation by G, so this G and G inverse product here, is still in this group H, then, I guess this should be N, bit of a typo, then you have a normal subgroup. So imagine that this says N here. So if you've got G and G inverse is in N, then this is a sufficient and necessary condition for it to be a normal subgroup. So this is the way you want to do it instead of actually proving that the two left and right cosets are the same. And I guess one comment is that despite the name, not all subgroups are normal. It's a bit of an abnormal property, if anything. So, as I promised earlier, we were kind of leading up to these quotient groups. So if we're working with normal subgroups, it turns out I can make a group out of this set of left cosets. So for a multiplication, I can literally just take the product of any two elements into subgroups, or subsets, I suppose. And what I get is something that's obviously a subset of G. So it turns out when I use this subset multiplication and I equip it on this group here where n is normal, so if I take the quotient of G by n, this thing here becomes a group. It's the quotient group of G by n. And the multiplicative structure is quite nice. So you take two cosets like this, corresponding to some elements G and G prime, you just get G prime n, so that coset there. And the identity is just n, and the inverse is, well, I guess it's exactly how you think it works. It's just the inverse element here, right? So it works kind of how you would expect. I won't go through this again, but there's a nice little slide here for intuition with these quotient groups in case they're a bit unclear. But to give you a summary, I like to think of quotient groups as kind of like a different way to view a group, but like losing some information. So there's some sort of intrinsic property of the normal subgroup you're quotienting by that removes differences between elements, but I won't go too far into that. One example, I guess the most common example of these, the most friendly, is that it turns out that these scaled integers as I was talking about not so long ago, they're actually a normal subgroup of the integers. So this z over mz thing that I was talking about as the remainder classes mod m, these things are actually cosets, and together they form a quotient group, I should say. Yeah, quotient group. So its elements are the sets of integers with the same remainder upon division by n. And so you can identify a remainder with the corresponding coset. So essentially now you're forgetting all of the differences between elements except for the fact that, hey, they have the same remainder, or hey, they have the different remainder, right? So this is a pretty common group, and we can see here that this actually has m elements, so that'll be important later on. So, won't be important right now though, because we'll do a more general example. This is one from the exam 2 years ago. So the setup for this is that I've got some normal subgroup n, and n is a subset of some not necessarily normal subgroup h. And I want to prove that this quotient here, h over n, this is a normal subgroup of G over n, if and only if h is actually a normal subgroup of G. So I want to prove that these two things being quotient groups are actually equivalent. So I suppose the normality condition for h on G is pretty simple. I just want to prove that GHG inverses in h for all G, H, and H. But the normality condition for h over n is going to be a little bit tricky. It's going to involve cosets. So maybe we might, as a first look, actually turn to the group G over n itself, because we know that this is a normal subgroup. We know that n is normal, and we know that, you know, we can do like this, right? So if I look at this and I look at, I guess, the coset that is going to be in h over n, then what I'm going to see is that GHG inverse n, if I look at this thing here as my first step, this is actually going to be a member of the quotient group G over n. So now I can go back, look at my multiplication structure on this quotient group, and I can actually write this thing here, this nice compact coset, as a product of cosets. So I can decompose it in this way, and then I can use the fact that this here is actually just the inverse of this coset Gn. So this thing here is ultimately where we're headed if we want to prove that this thing here is a normal subgroup of G over n, right? I need to show that this thing here is actually, again, a coset of h over n, right? So this is a nice thing, because this thing here, this GHG inverse thing, this is actually going to be somewhat connected to the normality proof of h, right? So in some way, we have established some kind of link between what we need to prove in order to show that h is a normal subgroup of G, And also what we need to prove if this H over N thing is a normal subgroup of G over N, right? So this is the nice link, and it's essentially just due to the fact that G over N is actually a quotient group, right? So I guess if I go backwards, so if I prove this if and only if this, just because it's a bit of a nicer direction to go in, H being a normal subgroup of G, this is basically just the same as saying that GHG inverse has to be an H, so that's the equivalent condition I showed earlier. But this proves, actually, because this is an element of H, I know here that any element of the form Hn, or any coset of the form Hn, that's going to be a coset, right? So I know immediately that this thing here is actually an element of this set here, H over N. We don't know necessarily that it's a group yet, but, or a normal subgroup of G over N yet, but this is what I can say. So I know that this thing here is now an element of H, so I know that this is at least a coset here. But now, I can use the fact that I identified earlier that this thing here is actually just this thing here. So it's this product of three cosets, and one of them being an inverse. But this condition that I've got now is exactly equivalent to saying that H over N is just a normal subgroup of G over N, right? So this thing here is exactly the normality condition for H over N. And that's basically it. So taking advantage of the multiplicative structure of cosets in a quotient group is really, really handy for proofs like this. Cool. Before I move on to homomorphisms, I'm going to quickly say this thing about abelian groups. So these will be covered more in Bruce's section, but I figure I'd mention them now. So an abelian group is one where the multiplication is commutative, right? So AB equals BA for all AB and G. A couple nice properties of these are that every subgroup of an abelian group is, I guess, obviously abelian, but more than that, it's actually normal. So all subgroups of an abelian group are normal. Every cyclic group is abelian, another one that should be, I guess, pretty clear. A group G is abelian if and only if you've got this identity here. I won't go too much into it. And another way that you can prove a group is abelian is if every non-identity element has order 2, then the group you started with had to be abelian, right? So these two nice ways to prove that it's abelian. So that ends the first bit. Now let's move on to talking about maps between groups, so group homomorphisms. So a homomorphism is just going to be any map between two groups which respects the multiplicative structure. So phi gh is just phi g phi h, that kind of thing. And again, as with groups and the multiplication, you basically just drop this star and this dot because we usually know what we're talking about most of the time. So that's kind of the defining property of a homomorphism, that phi gh is phi g phi h. A couple different types of them, actually many different types of homomorphisms. If it's one-to-one, you can call it a monomorphism. If it's onto surjective, then you can call it an epimorphism. If it's both, then it's an isomorphism, i.e. it's a bijective homomorphism. And in this case, we also say that groups are isomorphic, is if there is an isomorphism between them. And we use this, I guess in LaTeX it's the cong symbol, so I guess congruence. And an automorphism is just a isomorphism from a group to itself. So isomorphisms are pretty important. There's a bit of a spiel about them here. Essentially, it's just saying that two isomorphic groups are essentially the same in the view of group theory, right? So the only difference is that elements might be labeled a bit different, but the multiplicative structure is basically identical. A couple different types of morphisms, which you may have seen crop up in some proofs of things like the first isomorphism theorem and whatever. First one here, quotient morphism. So this is an epimorphism, it's surjective onto, whichever word you prefer, and it takes elements in G to the natural, I guess, coset of some normal subgroup, right? So this quotient morphism is often taken in respect to some normal subgroup. So if you project each element into its coset in this quotient group here, you get what's called the quotient morphism. Pretty handy for using when you're composing homomorphisms. And the inclusion is essentially just an embedding. So it's the identity, except you move one element, I guess, into another group. So it's not a very interesting map to talk about like that, but though simple, it's actually pretty useful in proofs. So a couple properties that you should probably have seen before are that we map identity to identity, inverse to inverse. The image of any subgroup is again a subgroup of H. Inverse is also an isomorphism. You map generators to generators. This one's a nice property, so you can occasionally make use of this fact that homomorphisms map generators to generators. And obviously the composition of homomorphisms is, again, a homomorphism, as you would expect. There's a bit more, so you could say more about isomorphisms, but we'll talk about those in a minute. So there's 3 isomorphism theorems. Okay, so an example of using homomorphisms. So this one's quite nice. This is showing that if I've got some non-trivial group homomorphism from some finite group G into the multiplicative complex numbers. So this is just the multiplicative group of the complex numbers, so I guess you throw out 0. Once you do that, you've got a group. And obviously this G is finite, as I said. If you actually sum all of the elements in G and then you look at their image under phi, then you actually end up with 0. So this is quite a surprising property, actually. Definitely surprised me when I first saw it. And this one here is a pretty tricky question. Like, if I just didn't have the hint here, it wouldn't be at all obvious how to do this. So I've included the hint as I think it would have to be given on an exam. The hint is that as a coset, Hg is actually just G again, if H is actually in G. So it's a property that you would have seen in lectures. I won't go bother proving it now, but as a coset, Hg equals G. So once you multiply by an element in this set here, you don't change it, right? So being that this homomorphism phi here is non-trivial, I immediately can say for free that there is some element in G, call it H, that doesn't just map to 1. So a trivial homomorphism is just going to be the one that sends everything to the identity. Obviously, we know that it has to send the identity to the identity, and a trivial map is often just a constant map. So for it to be trivial in this context, it just had to send everything to the identity. But because we know that it's non-trivial, we know that there is at least one element that has this property. So I basically just get that for reading the question, right? But the question is, how can I actually use this to end up here? Because that's still pretty far away. Well, I guess one thing I can say, one neat trick is, and it's kind of where we're going, if I've got 2 numbers, let's say xy, and this is equal to x, and y is not equal to 1, the only way that this is possible is if x is equal to 0. So if I multiply by something that's not 1, and I get the exact same thing, it has to be that this thing that I was multiplying was actually just 0. So the only way that this equation here is true is if x is equal to 0, right? So that's kind of where we're going, because we have that sort of thing here. So if we can somehow get phi of h to appear in this sum here, then I should be able to pull it out of the sum, because it doesn't probably depend on it. And then I will have teased out a factor of not 1 from this sum, and then I should be able to conclude that it's 0. So essentially where I'm going is that I want x to, I guess, be the sum that I'm looking at, and I want y to be phi of h, right? Because I know that phi of h is not 1. So if I was in an exam, that's kind of how I would start thinking about it. And the trick, or how you end up slipping in this factor of phi of h, is actually given in the hint. So the hint is that this sum here is over G, but equivalently I could write it as a sum over Hg. So just writing out the sum, I can use this hint here to say that this is really just a sum over all of the elements of this coset. And obviously elements of this coset are going to be of the form, I guess, Hg, where G is in G. So it's going to look something like that after I rewrite things. But now I know that this phi here is actually a homomorphism. So I can say that phi of Hg is actually just phi h phi g, right? And that's kind of, as I said, where we're going. We can now pull this phi of h out the front because it doesn't depend on this index variable here. But what I've got is I've got something here. It has reappeared after I've essentially multiplied by something that's not 1. So the conclusion, I guess, follows from the fact that phi of h is not 1. The only thing left to say is that this sum here actually just had to be 0, right? So this one's pretty sneaky. I think without the hint, this one would be pretty hard to come up with. Once you actually see it, it's not that hard, but like, I don't know. I feel like in an exam, you'd probably have to have the hint. So I thought I'd leave it in. But I think this is a really cool result, and probably something that would be fair game to ask in an exam, especially for the first bit. Cool. So moving on, a couple of sets associated with homomorphisms. We might have seen these before in linear algebra, so the terminology should be quite familiar. Maybe not fibers, although fibers are basically just pre-images from discrete, so it's just the pre-image of this function here with respect to some set. Although this set here has to be a subgroup. And you can talk about the kernel as well, which is just a special kind of pre-image. It's just the pre-image of the identity. So in this case, it's the set of all elements in G that map just basically to the identity in H, right? And it turns out that this is actually just a subgroup of G. And more than that, it's actually a normal subgroup, but we'll talk about that in a minute. And the image is essentially just take some set, right, and look at all of the function values you get after you apply the function to those elements. In this case, we're just looking at what's the possible set of values you get after you take phi of every element of G. And it turns out here that this is actually a subgroup of H. And we can't really say much more, so it doesn't turn out that the image is a normal subgroup, but yeah, it's still pretty cool. This image being a subgroup is actually really helpful. We'll use it later on. So, useful facts about kernels, as I mentioned, is that the kernel is a normal subgroup of G, which is pretty helpful. And I guess proving that, with linear equations, ax equal to 0 if and only if x is equal to 0 is enough to say that a is invertible, you kind of have a similar sort of thing for homomorphisms, which is to say that if the only element which maps to the identity is just the identity again, then your homomorphism is in fact one-to-one. It's a monomorphism as well. So this is a nice way of proving that something is one-to-one. So let's talk about a proof involving kernels. So let's say G is some Abelian group. I want to prove that every single subgroup of G is the kernel of a homomorphism from G. So I guess the fact that G is an Abelian group, if I remember back to what I was talking about earlier, I've actually got it on the slide here, any subgroup of an Abelian group is going to be normal. So I can say that for any subgroup H, which I guess I'm looking for a homomorphism which has this group here as its kernel, I know that this thing is a normal subgroup. So I seem almost coerced to look at the quotient group G on H, right? Because note that in the statement of the question, it hasn't actually said a homomorphism from G to some fixed group. We can actually choose whatever we want in the codomain. So we can send these elements in G to be, whatever, right? But we only need that it's a homomorphism and that it has this subgroup as its kernel, right? So I'm free to choose whatever other group to map to. And I guess here, the way that I would approach this in an exam is I know that any, subgroup of an Abelian group is normal, so I should probably look at the quotient group. So I'm looking for a homomorphism from G to G on H, but we looked at one of those earlier, which is actually just the quotient morphism, right? So if I made those two connections in the exam, I'd probably coerce myself to look at this quotient morphism as well. So I would want to look at this and say, maybe it has the kernel that I'm looking for. And it turns out that it actually does. So this is just the quotient morphism, as I introduced it a couple minutes ago. We know that it's obviously a homomorphism. And we also know that any element that's in the kernel of it, well, it maps any element G to the identity of G on H. But we know from earlier that's basically just H, right? So the quotient morphism of some element G just gives the coset GH, and I have that this G is in the kernel if GH is in fact H. Now, you might be able to tell right away that this actually implies that G is in H as well, and conversely, but we'll go through a rigorous proof of this, just in case that's not clear. So one thing I know is that obviously H is a subgroup, so it contains the identity, so I know that. And I know here that if G is in the kernel, then this is actually just the same thing as GH. So in fact, I can say that the identity has to be a member of this coset as well. But that implies that 1 has the form GH for some H and H, so I can write the identity as GH. But now all of these elements here have inverses, right? So in particular, I can say that G actually has to be H inverse in this case, right? And I know, obviously, that H is a subgroup, so this H inverse here is still an element of H. So in fact, this implies that G is in H, which is exactly what I said earlier, right? So this is just a bit of a justification for why this direction of the inclusion is true. The other direction is pretty clear, since, as we said before, even with the last example we went through, if you multiply some set here and you look at the coset with that element from the same set, you basically just get the set back again. So this is a pretty common property. So if you multiply a subgroup by some element, you don't change it in any way, right? So that proves the reverse subset inclusion here, which is enough to show that the kernel of the quotient morphism is exactly what we were looking for. So I guess the clues here, if I were in an exam to look for this quotient morphism, would be that any subgroup is normal. So it's pretty natural to consider then, what about sending elements in G to the quotient group? And then what's a common morphism from G to the quotient group? Just the quotient morphism, right? So essentially this problem broke down into what is the kernel of the quotient morphism? Which, if you happen to know, is pretty nice. If not, then I guess here's a way that you could go through proving it. So if you weren't sure whether the kernel was H, then you could do this. So the final bit that I want to talk about before I hand over to Bruce is the isomorphism theorems. So these are probably by far and away the most useful part of the first bit of this course. So these are used absolutely everywhere. And of these, it seems to be the case that the first isomorphism theorem is the king. So this is the one that you probably want to be using if you need one of the isomorphism theorems. So first isomorphism theorem says that if I start with any group homomorphism, G to H, and I look at the kernel, which we know to be a normal subgroup, then in fact what I end up with is that if I quotient G by the kernel of this homomorphism, which I know I can do, it's actually going to be isomorphic to the image of the homomorphism, which is to say that there exists an isomorphism phi from G quotient K to im phi, right? And as it turns out, this is the most useful of the theorems. So the second and the third isomorphism theorem that we'll look at in a minute are basically just corollaries of this. So if you don't really see why that's the case, I've got like, I guess, a mini proof or justification. I'm not going to go through it, so you can have a look at these on the slides once they're uploaded, or you can watch this recording back. But it turns out that this is actually a pretty nice way to just make this homomorphism, which we started with, an isomorphism. So the statement of the theorem is basically, how do I turn a homomorphism into an isomorphism? But I'll let you read about this later on. So let's use it to prove that there is no non-trivial homomorphism from ZMZ to ZNZ when M and N are co-prime, i.e. when they don't share any factors other than 1. So I guess why would I even think about using the first isomorphism theorem here? It doesn't talk about an isomorphism, and I'm not given a homomorphism to apply, so why would I consider the first isomorphism theorem here? Well, I guess if I want to prove that the homomorphism, if there was one, was trivial, I need to prove that its image is just a single element. It's just the identity, right? But I can just prove that the cardinality of the image is just 1. If I look back, this gives me one statement about the image. Namely, I can say that the image is actually just isomorphic to this quotient group here, right? So this is one way I can view the image, and then I can just use Lagrange's theorem maybe to get some sort of handle on the size, because one property I don't think I mentioned is that if you've got two groups that are isomorphic, they've got the same number of elements. So this isomorphism here will allow us to say that the image actually has the same number of elements as this quotient group. So that's, I guess, one way that I could think about it, because where I'm ultimately going is I want to prove that the image of this is just 1. So it's just the identity, right? So if I suppose I start with any homomorphism and I say that it's got R elements in its image, then the first isomorphism theorem plus Lagrange's theorem used afterward, if I use those two together, then I've got this implication here. So my G in this case is just Z over MZ, and my kernel is, I guess, clearly ker phi, right? And the image is, well, just M phi, but now I'm using Lagrange's theorem to look at the size of these two things. So the size of the image is just R, and I guess I can just use the fact that I can apply the cardinality to each of these on the top and the bottom. So I have that R times ker phi, if you want to write it like that, actually gives you Z over MZ. But this thing here has M elements, right? Because there are M remainders by N, right? M remainders by M. So this quotient group here has M elements. I think I mentioned that earlier. So if I look at this another way, I'm essentially saying that R divides M, right? Because I can write M as R times something else. But that's just saying that R divides M, right? So on one hand, I know that R divides M. If I can prove that R divides N, well, I know these things are coprime, so that would immediately say that R is actually 1, right? So if I can prove that R divides M and also R divides N, then I know immediately that R has to be 1, because they're coprime, right? So how do I now prove that this is going to divide N as well? Well, I can look at a theorem that I had a couple slides back, which was that this image here, another way of looking at it, is that it's a subgroup of Z over NZ, right? So this image here is going to be a subgroup of Z over NZ. So it's a subgroup of Z over NZ. So I can use Lagrange's theorem again. I know what Z over NZ's size is. I know that it's got N elements. So this implies exactly what I was trying to say before, which is that R also divides N. And I think from here it's pretty free, because like I said, anything which divides two coprime numbers has to just be 1, right? Because the only divisor they share by definition is 1. So why use the first isomorphism theorem in this case? Because I wanted a different way to look at the image, right? Where I was going is I wanted to prove that the image is 1. I guess one way I could do it is that if M and N are coprime, the only divisor it has is 1 in common. So that's sort of where I was going. I guess the other part I needed here was to realize that the image is actually a subgroup of the codomain as well. So in the end, we do indeed find that R is equal to 1, which is basically saying that phi is trivial. So I started with a homomorphism, I found that it's trivial, that proves that there are no non-trivial homomorphisms like this. This result's actually more true, like you don't just have to have Z over MZ. If this is any group and this is another group and their sizes are coprime, then the result's still true, right? I just picked these for nice effect. Right, last two theorems before I hand over. Second isomorphism theorem is, I guess this like fraction result that implies that things cancel out when you take quotients. So you've got two normal subgroups of G, one of them's a subgroup of the other, then you've got this relation here, H over N is a normal subgroup of G over N, and in fact, G over N quotient by H over N is actually just isomorphic to G over H. So all I'm saying is that quotienting is cancellative. So if we look at what this says about integers, then basically these are all just remainder classes. So these are remainders, I guess this one here is going to be the remainders by N, this one is the remainder by M, this one here is the remainder by N, but only amongst things that have multiples of M. And what I'm essentially saying by the second isomorphism theorem is that if I reduce modulo N first, and then I reduce modulo M, which I guess is this bit here, then I may as well have just reduced modulo M in the first place, right? So if I do these two modulos, then I'm ultimately going to get the same thing as if I just done the last one from the beginning, right? So that's, I guess, the intuition for the second isomorphism theorem. This one's not too useful in this course, although I won't say that it's a useless theorem, because I think that it's useful elsewhere. It's just not at our level yet. So, final result. The third isomorphism theorem says that now, if I've got a normal subgroup and some other subgroup, not necessarily normal, and with no necessarily relation to n, then this subset multiplication here is actually a subgroup, and the intersection of h and n is a normal subgroup of h, which I guess sort of follows because n is a normal subgroup. And moreover, what I can now say is that these two quotients, so the product hn, quotient by n, is isomorphic to the quotient of h by the intersection with n. So that's what this third isomorphism theorem is saying. Again, I've got some intuition here. I won't go through it, but this is just sort of explaining how this theorem comes about, or like the logical intuition. So, final thing I'll do before I hand over to Bruce is I will go through an adapted example from one of the really old class tests. So this is not exactly how the question presented. The original question also wanted you to prove this thing that I'm just going to give you for free, which is that if I'm working with GLN of C, and I look at this subgroup of all of the scaled identity matrices by some non-zero complex number lambda, this actually ends up being a normal subgroup. So I want to find a quotient of the special linear group such that this quotient here is going to be isomorphic to the general linear group quotiented by this identity subgroup n. So why would I use the third isomorphism theorem here? Well, I guess I know that SL is a subgroup of GL. So I guess in here, SL is kind of playing the role of H. And I've been given a subgroup of normal subgroup of GL for free. So I know that N is a normal subgroup. So that's playing the role of N here. So I would sort of think that I should probably be using the third isomorphism theorem because I've got those conditions, right? So if I saw this in an exam, then I would probably think, well, I've got a couple ingredients here that seem to suggest that I could apply the third isomorphism theorem. So if I look at what the third isomorphism theorem here says that the product of SL and N, quotient by N, is going to be isomorphic to SL, quotient by SL intersect N. So that's what the third isomorphism theorem gives us here. So I guess our work now is to find out what this is and what this is. And I guess one way that we're going is that, well, this here is probably not all of n. So since I'm looking for a quotient of GL over n, this thing here is probably what's going to end up being GL. And in fact, that's exactly what we're about to prove. So it should be pretty clear that if I take this product, this is at least a subset of GL, because GL is going to be the set of invertible complex n by n matrices. SL is going to be the set of all matrices with determinant 1. And I know that because my choice of lambda here is non-zero, that this scaled identity matrix here is non-zero, so it's not the zero matrix. Therefore, it's also got non-zero determinant. So if I multiply these two together, I get another invertible matrix, so I clearly stay within this GL here. But I now need to prove, or I guess I am trying to prove, that the other direction is also true. So if I want to prove the reverse inclusion, I will start with some matrix M in GL, and I'll just call its determinant D. So D for M, and we know that this is not going to be 0. So I want to prove that M here is actually part of this product here. So I guess I need to write it as the product of a matrix of determinant 1 and some multiple of the identity matrix for some complex number. So one way I could do it is if I let my constant that will be multiplying the identity matrix just be the nth root of D. So the nth root of D might be complex, but that's okay because we're working with the complex numbers. Then I can write obviously M, just M times the identity. That's sort of the property of the identity matrix. I can now tease out a factor of lambda by essentially saying that, well, 1 is just lambda inverse times lambda, and then I can use the fact, well, these are constants, so they associate with this product. So in fact, I can say that lambda inverse M times lambda I is just the same thing as M. So this here is going to obviously be the matrix that belongs to N, and this thing here would probably be the thing that belongs in SL. So I need to prove here that this one here has determinant 1. So I guess clearly this one's nice and easy. This one's an n. But it's not at all clear why this should be the case. But in fact, it's actually pretty clear once you look at what we defined lambda to be. So the determinant of lambda inverse times m, if I've got a constant here, I basically pull it out, and because I'm doing a determinant of an n by n matrix, I have to raise this constant factor to the power of n. So that's a property of the determinant that you might have seen before. But in this case, det m, that's just going to be d, right? And lambda to the negative n is actually going to be 1 over d, right? So it's going to be 1 over d. And obviously, if you multiply those two together, you get 1. So this is indeed a matrix with a determinant 1, so it sits in SL. So it's exactly what we were trying to prove, that SL times n is actually just GL. And I guess also we have, if we look at this intersection, the other thing we had to look at, we want all of the matrices of determinant 1, and all of these has to be of the form lambda I, so they have to be some sort of scaled identity matrix. That's essentially another way to write it. I want scaled identity matrices of determinant 1, but the determinant of these guys is just going to be, I guess I'm using omega here because I'm going towards, I guess, something that looks a bit like roots of unity. This here is going to be omega to the n, right? So it's an n by n matrix, n by n identity matrix. It's just the product of all the entries along the diagonal, and those are all going to be omega. So this is just going to be omega to the n equals 1. So I guess omega here has to be an nth root of unity. So there we go. That's my quotient. I take the matrices of determinant 1, and I quotient by all of these scaled identity matrices by some root of unity. And that's the quotient I'm looking for. And that also ends my part of the talk. So I will hand over to Bruce now. There will be a slight interlude where I have to stop streaming and he has to start streaming. Good luck with your exams. Hopefully this first bit was informative. And now for the rest of the talk, we'll be going over direct products and the group actions before, on Thursday, like I said, we move on to rings and fields with Gerald. So I'll see you all.
Alrighty, so thanks, James. As James mentioned, I'm Bruce, and I'll be going over the second half of this talk, which is about direct products and sums, and also about the second part, which is about group actions. So just a disclaimer, I'm coming over to you from the big bad land of COVID isolation, so apologies that my voice isn't quite what it could be, and I might need to pause at times just to get some water, so do just bear with me for a second. Okay. We will begin, though, with direct products and sums. So first of all, we've got external direct products. And this is actually something we've seen before, because we've seen things like we've got a set A, and we've got a set B. And what you can do is you can do A times B, that's the Cartesian product. It's just a pair of numbers where one comes from A, and the other comes from B. And that's what A times B is. It's exactly the same thing with G1 all the way down to Gn. If we have these groups, if you take the Cartesian product, then basically what you're doing is you're taking one element from each group. Right, and so this is actually the Cartesian product. But this product is also actually a group itself, right? And so how do we actually define the operation on this group? Because every group needs an operation. Well, what you do is you say, let's define an operation between two elements of this form. So we've got, this is in G1, this is in Gn. Right, define an operation, it's just the same as before. Right, so if you do the operation G1 with H1, then you just do the operation in that group. And that's what's called coordinate-wise multiplication. So coordinate-wise multiplication. Right, all we do is we just take these individual elements and we operate on them as we would in that group. And that's what's called an external direct product. Right, so as an example over here, right, just as a very simple example, we've taken G as the standard set R+. and that's a standard group under multiplication. And if we do like 2, 3 operated on 4, 5, we just multiply them individually. So 2 times 4, we get 8, and 3 times 5, we get 15. Cool. So with external direct products, there are also homomorphisms we can define based on them. One is called the projection. So let's just say we have a nice set of groups here. So G1 times G2, all the way down to Gn. And let's just say we want to pick one of these, so Gk. Right, and so what a projection basically is what we do is we take any element in this Cartesian product. And we say, let's map this to just this element. So just pick one of the elements and map it to Gk. Right, that's what a projection is. Because you're basically projecting this big group onto one single group. It'll be projected onto Gk. Right, and that's what this is. It's called the canonical projection, πk. It maps this massive product of groups down to Gk just by selecting Gk. Right, and when you think about it, James walked us through the two big names that we use to associate with morphisms. This is actually an epimorphism because it's surjective. We can get any element of Gk because, well, you can just take, if you want a certain element of Gk, then basically you can do whatever you want over here. As long as you have Gk in that in the relevant coordinate, that will definitely map to Gk. And that's why it's an epimorphism, because it's surjective. And the canonical injection is injective. Right, and so what it basically is you take one element and you project it onto the product. You project it onto the external direct product. Right, and what you do is basically you don't want to add any extra information, so you just fill in the rest of the columns, fill in the rest of the components with the identity. So you don't want any new information. Right, and so this is injective as well because, well, you don't lose any information when you get from there to there. You keep all the information about what Gk is. So it's called a monomorphism. Right, and all the non-kth coordinates are set to the identity. And we use the Greek letter iota. So, when we think about the canonical projection for this example, let's just say we're doing pi2. Well, remember pi2, right, projections, we just ignore everything except for the second element. So who cares about this? No one cares about that. Basically, this is just equal to 3. That's the canonical projection. Canonical injection, we have to map this to the product, and what it does is it says, let's keep the -5, but everything else let's just set to the identity. So just be a bit careful with what the group is over here, because we have a bunch of different groups over here. What is the identity of each one? Well, this one is R star, that's going to be 1. This one is just R, which means it's the additive group, 0. And this one is S4, which means it's a symmetric group, which means it's just going to be equal to the identity transformation. Cool. Yeah, so that's external direct products. You'll move on now to internal direct products. So internal direct products, basically what we're doing is we're considering different groups here. And as you can guess from the word internal, we don't want to create a new group from these groups. So you remember from before when we're taking G1 down to Gn, we're mapping them to a completely new group, G1 times Gn all the way down to Gn. Right? In this case, we don't want to create an entirely new group. We just want to take these groups and use it to form another subgroup of G. Right? So all of these groups, G1, Gn, they're a subgroup of G, but we don't want to create a new group. We want to use these groups and somehow map them to another subgroup of G. But to actually be able to do that in a meaningful way, we need two conditions. So first of all, the elements of the different groups need to commute. So that way, if you have, say, G1 from group 1, G2 from group 2, all the way down to Gn, you can rearrange them however you want and nothing will change. That's this first condition. And the second condition we need is somehow they need to be disjoint in a way. So what do I mean by that? Right, we've got for all I, so basically for all the groups, the intersection between that group and the product of all the other groups needs to be equal to the identity. So what that means is that you shouldn't be able to take elements from the other group, multiply them, in order to get an element in this group. So they're kind of disjoint in a way, right? And the explanation written here is it's impossible to get any non-identity element in one subgroup from taking elements in the other subgroups and multiplying them together. Right, and once we've done that, when we think about it, we actually have something called the internal direct product. Right, and the way we form that is simply by doing this. So it's going to be the set G1 down to Gn. And that's going to be equal to the set this. Right, and basically what that is, it's the group that you get from multiplying all of the elements together. Right, and you can kind of see why it's isomorphic to the external direct product, because in this group, right, because these elements are kind of disjoint, right, this condition number 2, the elements are disjoint, it means that, right, all of this information, we can actually recover what G1 is. We can also recover what G2 is. We can recover what G3 is, because none of these elements interact, none of these elements intersect. So just from this product, from knowing what the product is, you can actually tell me exactly what G1 is, what Gn is. Right, and so the formal way to write that is that the homomorphism from the external direct product to the internal direct product, where we basically take all of these elements and multiply them together, is a bijection. Because once you multiply them, right, you can still recover the original elements because of condition 2, right? You can't get to any element of G1 from multiplying all of these things together. Right, and so that's our first example down here. Right, so once we've got that, we've got the internal direct product. Right, and so there's this theorem that we have over here associated with the external direct product. If you take the product of two sets and you divide it by 1, and by 1 we mean just the set with just the identity, 1 times h, that's isomorphic to just G. Because as James mentioned with the intuitive explanation of quotients, what we're doing is we're taking the set G on H and we're dividing it by 1 on H, which means we're kind of forgetting all the information we have about H. Right, and so we're just basically left with G. But something else we should keep in mind is that it doesn't work the other way. Right, you can quotient out products, but once you do a quotient, you can't always get back to the original group just by doing another product. You can't always write G on H times H is isomorphic to G. So we'll do an example just to show that. So prove that it's not in general true that G on H times H is isomorphic to G. So just remember that it only goes one way. So this product quotient equivalence only goes one way. We can't always say this is true. Right, so how would we prove that it's not in general true that these sets are isomorphic? Well, let's just go back to a bit of a theorem for disproving group isomorphisms. So it's useful to know that if you have an isomorphism, right, between two groups, then if you take one element and you map it to something else using that isomorphism, then those two elements have to have the same order. So what we can say is basically isomorphisms preserve orders of groups. Right. The second thing we can know is that for G is abelian, G prime abelian, it means that if two groups are isomorphic, then basically they must both be abelian if one of them is abelian. Right, so it preserves commutativity. Last of all, these two things. So if you've got H a subgroup of G, then if you map it to something, so you do phi of that subgroup, then that's also a subgroup. And we also preserve normality, right? So if it's a normal subgroup, then then phi of that same subgroup is also normal. Cool. So these are 4 theorems, and why do I say that these theorems are useful for disproving group isomorphisms? Because what you can do is you can say, let's take two groups, A and B, and we want to somehow show that they're not isomorphic. Well, what we can do is we can say, let's just say if A has 2 elements of order 3, for example, and B doesn't have 2 elements of order 3. Well, what that proves is basically because this isomorphism must preserve orders, that can't be possible. They can't be isomorphic, because then every element of order 3 needs to be mapped to another element of order 3 in B, right? So there's something not quite right, if we say that these two are isomorphic, right? So these kinds of properties are useful because we can say, for example, if B is not abelian, A is abelian, well then also they're not isomorphic. So this whole idea of these four properties is we can basically, if we can identify cases where they don't hold, then we can disprove isomorphism. Right. So maybe let's do an example. And in this particular example, we can take a very simple set of groups. Let's just take Z on MZ times MZ. Right, so just remember this is an external direct product. So what that means is that we've got one element from Z on MZ, which as James took us through is just the remainders on mod M. So for example, we could have MZ plus 1, MZ plus 2, and so on. And we also take elements of MZ. So this could be M, it could be 2M, it could be 7M. But the whole idea is just basically this external direct product, we're just taking one element from that one and one element from this one. And somehow we need to show that this is not isomorphic to, well, what would it be in this case? We're basically saying that this is not cancellative, so we need to somehow prove that this is not isomorphic to Z. Okay, so let's think about that for a second. We want to basically take this group and identify elements of the structure, so elements of these four things that we talked about that do not hold for G. So one useful thing about Z is basically every element has infinite order, or order 0. Right? Every element except for 0 does not have a finite order. Right? Because you can take 1 and you can keep on adding it to himself. Right? You can keep on saying 1 plus 1 plus 1 plus 1. And in Z, you'll never get down to 0, which is what we want. So is this also true? Because if Z has no element of finite order, then if we can find an element of finite order in this first group, then we've shown that they're not isomorphic. So, for example, let's just take this. Well, MZ plus 1, that actually has order M, right? Because if you add MZ plus 1 to itself M times, then the 1s all add up and you get MZ. Right, so what that means is that basically MZ plus 1, and, well, the second one can be whatever we want. It can be 0. Well, that has order M. Right, so basically we've shown that there's an element in this set that has order M, but the same is not true of Z, because no element in Z can have order M. Right, so we can just write this all out. So Z on MZ times MZ has an element of order M, but then none of the elements of Z do have order M. Right, and so what that means is that isomorphisms, because they preserve orders of elements, it can't be true that this is true. And so we've proven this is not always true by counterexample. So one thing we should mention is that the wording of the question here is quite important. It's saying it's not in general true, which means you can disprove it just by a single counterexample. But if you're trying to show that, for example, this is never true, then you can't use a counterexample. You'll need to do a direct proof and somehow show that in general, right, these can't be isomorphic. In this case, it's enough just to do a counterexample. Cool. Yeah, and so as James touched on, I'm going to be talking a bit more about Abelian groups. So in an Abelian group, we actually use addition instead of multiplication, generally. So for example, from before, we could have G asterisk H or GH. But in an Abelian group, we might prefer just to say G plus H, right? And we do that to indicate that the plus is generally Abelian, because then G plus H equals H plus G, and it kind of makes a bit more sense. So, well, with the internal direct product, so remember that thing where we take G1 all the way down to Gn, if you do the same thing for Abelian groups, it's called a direct sum, right? And in particular, we write it a bit like this. So, if these are all subgroups of the Abelian group G, and they generate G, then we say that G is the direct sum of all of these groups, and we write it like this, this nice sign, plus sign, Gi minus 1, Gi plus 1, down to Gn. Basically, the intersection of this is equal to just 1, right? Meaning that you can't actually get any of the elements of G1, Gi, from the other elements G. Right, so it's the same kind of thing over here. We want to show that it's a direct sum if and only if the only solution to elements from each group, so A1 is from G1, A2 is from G2, all the way down to AN is from Gn, if and only if the only solution to all of these things adding up to 0 is if all of them are equal to 0. So that might remind us a bit of linear independence, right? The idea is that if you take elements and you combine them from multiple different sets, then, you know, the only solution is if all of them are equal to 0, right? Because you can't actually get any of these individual elements from other elements in the set. So for them to all equal 0, for them to add up to 0, they need to all be equal to 0. Right, so this is an analog to the direct sum. And it's a very important theorem because it's often the simplest way to show that something is a direct sum. Let's do an example. So an example with Abelian groups. And we've got two Abelian groups such that the direct sum of them is equal to G. And somehow we want to show that the order of the sum of these two elements, for one being from A, the other being from B, we want to show that the sum of those two elements is equal to the lowest common multiple of the individual orders. Right? So when we're dealing with a question like this, we might want to think about what it actually means for an order, or what an order actually is. Right? An order n, in this case, is the smallest number n such that n times a plus b is equal to 0. Right? Remember from before we did orders with normal groups, so g to the power of n is equal to 1. But now we can actually write it, instead of g to the power of n, we write it as ng is equal to 1, is equal to 0. Right? Because we change powers to just multiplication, and we change the multiplicative identity 1 to the additive identity 0. So looking back at this, basically we want n such that n times a plus b is equal to 0. Right? So that's what we're doing over here. So this is actually the order of a plus b is the smallest positive integer value of n such that n times a plus b is equal to 0. Right? And so our instinct is to expand this, so na plus nb equals 0. So basically we're trying to find n such that this holds. And at this point we might start to think, hang on a second, we've got a plus here. Why don't we use the property of a plus b equaling g? Right? So remember, a plus b equaling g means that the only solution to a plus b, with this one being an element of a, this one being an element of b, equaling 0, is if both of them are equal to 0. So having now seen that, we know that na is an element of a, right, by closure under multiplication, under addition. So is nb an element of b. So, well, we've got exactly the conditions we need, right? That means that na must equal to 0, and nb must be equal to 0, right? If this is to be true, right? So, yeah, so g is a direct sum of a and b, which means that basically both of these need to be equal to 0. And now we start to think about the individual orders of a and b. So, well, we want to express the order n, so express n, in terms of order of A and order of B. Right, so what that means basically is we want to express this number n in terms of the individual n's that we need for this to be equal to 0. So, for example, na equals 0 and nb equals 0. That means that n must be a multiple of the order of A, right? Because, well, this single sentence, it means that n must be a multiple of the order of A. Sorry, that's my COVID voice getting in the way. Yeah, so over here, we also need n to be a multiple of B. So, yeah, combining those two, it seems like the conclusion follows, right? Because then for n to solve both of these equations, we need it to be a multiple of both order A and order B, which means that it needs to be a multiple of LCM order A and order B. Alright, so reading out the entire proof, for a positive integer n, na equals 0, if and only if n is a multiple of this order. And same thing over here, nb is equal to 0, if and only if n is a multiple of this order. So, well, for both of them to be true, we need it to be a multiple of the LCM. So we're proven. Cool. I might get some water, just give me a moment. works. My voice is mostly restored. Okay. So we'll look at a very similar example here. So consider the group G generated by 3 elements. And it might look a bit intimidating at first, but this is actually a very common thing we'll see. X, Y, X inverse, Y inverse equals 1 basically means if you multiply through by Y, then you multiply through by X. Yeah, so it actually just means that they commute. So X and Y commute. Same thing over here. This just means that X and Z commute. And lastly over here, this means that Y and Z commute. So nothing too shocking over here, but basically we've gotten that they all commute. But we've also got this requirement, x to the 5z equals y to the 3 equals 1. And so somehow we need to find out what the group generated by those 3 elements is going to be equal to. So yeah, they all commute, and that means that we can express G as being equal to y to the m times x to the n times z to the k, for m and k are elements of z. Because if they all commute, then we can set a certain order of x, y, and z, and then that won't change anything. So this is we won't get any new elements by allowing, for example, z to the k times x to the n times y to the m. Right, this is pretty comprehensive because they all commute. Right, so that's the first thing we want to work out. The next thing we want to do is kind of use these two things. So use the fact that x to the 5z is equal to y to the 3 is equal to 1. So the first thing we'll do is think about x to the 5 times z equals 1. So if x to the 5z equals 1, that means we can remove x to the 5, we can divide by x to the 5z, and it won't change anything. So this general form of the elements in our set, we can, for example, divide by x to the 5z. We'll get ym, xm minus 1, zk minus 1. Oh, sorry, I have to do n minus 5. And that'll be the same element. Right, we can keep on doing that. And, well, we can keep on doing this until z becomes 0. And basically, we've eliminated z. Right, so in particular, y to the m, x to the n minus 5k, times z to the k minus k. And that's just equal to y to the m, x to the n minus 5k. Right, so what does that actually mean? It means that z is just a distraction. Right, z doesn't actually add anything to our set, because we've got this relation here. So we can actually express g as just being equal to the product of a power of y and a power of x. Right, so that's pretty good. We've reduced it so far. And you can probably guess that at this point we want to start using y to the 3. Right, in particular, we've got, this is a typo, it should be this over here. But before we go into that, basically what this means is that we've got an internal direct product. We've got an internal direct product of the group generated by y and the group generated by x. Because we know that x and y, they don't actually interact because we're just given these formulae. And whenever we're given these formulae, all it means is just that there are no other relations. So it means that y and x are different, they don't interact. So this group is actually equal to the direct product of y, the group generated by y, and the group generated by x. Right, and so that's actually isomorphic to the direct product, the external direct product. And then when we think about it, right, there is no relation given for x, right? X is just equal to, well, we can have x squared, x cubed, and so on. We can also have the identity and x inverse, right? It's just equal to z, right? It's isomorphic to z because x is infinite order, right? Same thing over here with y. So y is a bit different though, because we can have 1, we can have y, we can have y squared, but then we know that y cubed is equal to 1, so then we stop there. And this means that it's equivalent to z on 3. Right, so yeah, basically we've shown that because the internal direct product is equivalent to the external direct product, and because y has order 3, and z has infinite order, right, we've got this equivalence here. Cool. So that's a bit of a trickier example with some more complex equations, but it just shows how useful the internal direct product is. Cool. Alrighty, so with that, there's actually something else we can show. We can show that all the cyclic groups, or all finite abelian groups, can be expressed as a direct sum of cyclic groups. But to actually get to that point, we need a few theorems. So first of all, we'll discuss how to talk about cyclic groups themselves. Right, so all cyclic groups, and we just kind of touched on that a bit before. So cyclic groups are just groups generated by one element. They're equal to Z or Z on M for M a positive integer. Right, and there's a bit of a note here that Z can be thought of as Z divided by 0. So we can also just in general say that all cyclic groups are Z on M for some integer M is greater than or equal to 0. So some examples here. This group over here. So if you've got the set of nth roots of unity, if you remember from your algebra or for your first year algebra days, this is equivalent to the smallest cube root of unity, so e to the I 2 pi n. Then you do the square of that one. And basically you keep on going up until you get to e to the I n minus 1 pi n. And then you get back to 1. Right, so basically this is the same thing as a cyclic group of order n, because you've got this one group, and you've got its, well, let's just write it as z, and you've got z squared, and you've got all the way up to z to the n minus 1. Right, so this is actually isomorphic to z on n. Cool. And another example is the group 2 to the n, for n is an integer. Well, what is that group? It's equal to, well, for example, n equals 1, we've got 2, and we've got 4, 8, 16, and so on. Then we can also go backwards, right, because we can have any integer. There's also 1, a half, a quarter, and so on. And you can see it kind of goes on forever, and it's isomorphic to z, right, because we've got this thing 2 to the 1, 2 to the 2, 2 to the 3, and so on. And that's isomorphic to z. And in general, you can say if you've got an infinite cyclic group, it's isomorphic to z. If you've got a finite cyclic group of order n, it's isomorphic to z on n. Cool. So to break a finite abelian group down, the first thing you can do is to break it into generating subgroups, which we call the p-parts of the group. Right, so what is a p-part? Let's think about this. It's actually the definition of a p-part is all elements of this set such that p to the n times a is equal to 0 for some n is greater than or equal to 1. Right, and what that means is that the order of a is some power of p, right? So the order is some power of p. So for example, you've got p equals 2, right? If you've got an element of order 2, element of order 8, element of order 4, and so on, then that constitutes your 2-part. And it turns out that the 2-part or the p-part of a is a subgroup of a. Next thing we do is we can actually work out that a can be decomposed into its p-parts, right? So if you've got the prime factors of the order of a as being p1, p2, all the way down to pn, then a is equal to a of p1, a of p2, plus all the way down to a of pn, right? And so this is actually kind of broken down into all of these small parts. But yeah, that's how we decompose a into p-parts. And so what's useful to notice is that each of these p-parts has order or size p, p1 to some power, right? So for example, if the order of a is equal to like 25, or the order of a is equal to, let's say 25, then, well, it has to have a 5-part, and the 5-part needs to have order 25. We'll get into that more later, but basically this is related to the orders of each of the p-parts. So yeah, we've established that a finite abelian group, you can decompose it into a direct sum of the p-parts, but you can actually decompose all of these p-parts even further. And what's really interesting to note is that if you take a p-part, so G equals AP, the p-part of some finite abelian group A, then you can actually write G as a direct sum of cyclic groups, right? So that's where our cyclic groups from before came in, because now we know that every group can be written as a direct sum of cyclic groups. In this case, each of the cyclic groups has order equal to p to some power. So you can see it over here. G is isomorphic to z divided by p to the power of n1, all the way down to z on p to the power of nk. And all of these integers are greater than or equal to 1. Right, and so another thing is that for a given group, the orders of these cyclic groups, so p to the n1, p to the n2, p to the nk, they must always be the same up to ordering. right? So for example, you can't have a group being isomorphic to z on 2 times z on 2, and then also isomorphic to z on 4, right? Because the orders of these individual cyclic groups must always be the same. So this is not possible. Right, so let's put it all together though. How would we use this to find all the finite abelian groups of order 360 up to isomorphism? And this is a very common type of question, because basically what we're looking at is how do we take any abelian group of order 360 and break it down into its p parts and then subsequently its cyclic groups. So what we do is we say, let's take all the p parts, or the prime factors of A. In this case, we've got 2, we've got 3, we've got 5. And what that means is that we've got a 2 part, we've got a 3 part, we've got a 5 part. And that's the first step over here. Identify those primes that give us the p parts. Okay. And so what we notice is that each of these needs to have order equal to the part of this prime decomposition that is made up by that prime. Because something that wasn't explicitly mentioned, but if you have A plus B plus C, then the order of this needs to be equal to A, order of A, times order of B, times the order of C. So that means that the part of this order that comes from 2 needs to be embedded in this 2 part. Same thing over here. The order here that is made up by 3 needs to be embedded in the 3 part. And same thing with this. Right, so basically you've broken this down. A2 is equal to 2 to the 3. A3, 3 to the 2. A5, 5 to the 1. And what you want to do is try to break this down into cyclic groups. So if we've got a big group that has size 2 to the 3, then, well, that group can be written as the direct sum of cyclic groups, z on 2, z on 2, z on 2. Right, because then each of these will have order 2, and the total order will be 2 times 2 times 2 equals 8. But you can also do it another way, right? There are other ways to partition these powers, and we know that they're distinct, right? Because of the previous theorem. So z on 4, z on 4, z on 2. So these are 2 distinct possibilities. And what you want to do is basically, you can see it over here, basically find all the ways to partition this factorization into different groups. So you can have A2 is isomorphic to z on 8, or z on 4 plus z on 2, or you can break it down completely. Same thing over here, you can just have 1 z on 9, or you can break it down into 2 parts. This one is just we've got 1, 5, so there's only one option. And what you'll work out is that each of these represents one combination for the p part, right? So in total, how many options are there for A? Well, we can have 3 options for this, we can have 2 options for this, and 1 option for that. So the total number is actually equal to 6. Right, so if the question did ask for the total number of finite abelian groups of order 360 up to isomorphism, you would say 6 because there are 3 options for over here, 2 options over here, and you basically mix and match from the different options. Cool. And this is a bit of a tougher example that requires a bit more proof, but basically we're assuming that G is a finite abelian group of order n for some positive integer n. And we've got a map pi d such that pi dx is equal to dx. And remember, this is not equal to a product, it's equal to x plus x plus x by itself, d times, because we're working in an abelian space. Right, and so basically we want to work out when this is an isomorphism, and your criterion should be a simple condition involving n and d, and prove that your criterion is correct. So it's a bit of a more involved question, and what we often do here is we think, well, intuitively, if you've got pi of d of x equals dx, and you've got a group of order n, well, intuitively, right, if we think about this, if d and n share some common factors, we're probably going to lose some information when we multiply by d, right? And if they don't have any common factors, we've kind of seen this before with modular arithmetic, we're probably not going to lose much information. So it's often good to start off with a condition and see if we can prove it. So condition is GCD and d is equal to 1. And something to note here is that we want to show 2 things. We want to show that basically this is an isomorphism if and only if the integer holds, the condition holds. So in this case, we want to show that if it's not true, if our condition is not true, then it's not an isomorphism. And we also want to show the converse, which is that if it is true, then it is an isomorphism. Cool. All right, so how do we show something as an isomorphism or not an isomorphism? Well, it turns out that something being an isomorphism is equivalent to the kernel being equal to this trivial subset, right? And that's something James mentioned earlier, right? And so when we think about it, right, what does that actually mean? If the kernel of this is equal to, is trivial, it means that dx is equal to 0 only if x is equal to 0. Which means that no element has an order that's a factor of d, right, except for 0, right? So we can't possibly have an element with order d. We can't possibly have an element with order d on 2, because then dx would obviously be equal to 0, right? So basically we want to show that if this condition holds, then it's exactly true that no element has order a factor of d. Because if it's a factor of d, then, well, once you get to dx, then that's equal to, well, for example, if d is equal to m times n, then if the order of x is equal to m, then, well, once you multiply by n, you'll also get 0 as well. Right, so if an element has an order a factor of d, then dx will also be equal to 0. So what we often do with these kinds of questions is we think, let's first try to show, the first part of this is showing that GCD ND is not equal to 1 implies that this is not an isomorphism, i.e. that the kernel is not trivial. Right, so let's just first say that the GCD is not equal to 1, which means we can start to decompose it into primes. And so it's really useful to use this prime definition, this p-part definition, because if GCD and D is not equal to 1, then they must share a prime in common. And what we can do is we can isolate that p-part, so pi, and start to think about whether there is an element with order a factor of d. So, yeah. So consider any prime factor of n, which is pi. And think about API, right? The API is isomorphic to a direct sum of individual elements of this form, right? So we've got n1 plus z on pi to the power of n2, all the way down to z on pi to the power of nk. Right, so remember that from before, it's isomorphic to this direct sum. So when we think about it, right, we've got to have some element that has order pi, right? Because let's just say we will take this, for example, z on pi to the power of 1. Well, this is actually equal to 0, 1, all the way down to pi to the power of ni, right? Which means that if we actually divide one of these elements, so just take, this should go up to pi to ni minus 1. If we actually take, for example, pi to the power of ni minus 1, then if you multiply that by pi, you get pi to the ni, which is equal to 0, right, in this equivalence class. Right, so that means that almost certainly there is an element of order pi, no matter what. Right, so more formally written out, let's just write this out. There must exist in this p part some element g of order pi to the power of k. And then we know that once we multiply this by pi to the power of k minus 1, then that must have order pi, right? Showing the existence of an element of order pi. Which means that almost certainly, if d shares any factors with n, then we can pick one prime factor that they have in common, and then find an element with order p that divides d, right? P divides d. Right, which means that the kernel of pi d cannot be trivial, right? Because, for example, if they have common factor 2, which we are assuming, if n and d have common factor 2, then we can find an element of order 2. And then we can show, essentially, that 2 to the power of, we can basically show that that element satisfies dx is equal to 0, because d is a multiple of 2. Right, so if d shares any factors with n, the kernel cannot be trivial. But we also have to show the flip side, which is that if the GCD is equal to 1, then pi d is an isomorphism. Right. So suppose that this is true, suppose that the GCD is equal to 1. Right, and so when we think about it, the orders of all the elements of G must divide n. Right, so that's just a kind of property of G. Right, so if we've got G, we've got an element x, the order of x needs to divide G. Because, and that's just a common property we know. Right, so that means that if, for example, we do have this property where the GCD is equal to 1, then for dx to be equal to 0, that means that the order of x divides d. But we also know that the order of x divides n, so these two combined tell us that the order of x divides the GCD of n and d, which means that the order of x is equal to 1. So yeah, basically what we've shown is that the only element that satisfies this is x is equal to 0. So going down, we've shown that if GCD of n and d is equal to 1, then the kernel is trivial, and therefore this is an isomorphism. So basically we've shown both of the directions. We've shown that if it is equal to 1, it's an isomorphism, and we've shown if it's not equal to 1, it's not an isomorphism. Cool. And we don't have time for this, but it's an interesting question, and we will leave it as an exercise, because it's quite a nice question to try. But we'll move on now to group actions. So group actions we've got are basically what happens when we take a group and we use it to act on a set. But before we talk about that, we'll talk about one type of group actions called isometries. So the group of isometries is a set of all isometries, right? And that's basically a set of functions that preserve distance, right? So it means that if we've got x and y, and you map them to tx and ty, then the distance between these two, which is this, will be equal to the original distance between them. And that's something we've hopefully seen before. And all isometries can be written as this linear equation, T of v is equal to q of v plus c, for some orthogonal matrix q and some vector c. And the idea is that if we actually write this thing, this is the set of all isometries that fix the point 0, which means that for tv equals qv plus c, because 0 has to map to 0, we know that 0 is equal to q0 plus c, which means that c has to be equal to 0. So basically this is a set of all isometries in this form. Right, and the c is gone. Right, so it's essentially a set of orthogonal matrices as well. So something interesting about O2, and remember O2 is going to be the set of isometries fixing 0 in R2. Right, it's a set of isometries fixing 0. Right, so what this means basically is that if you look at this graph, if you take any isometry, then let me just draw this again. If this isometry fixes 0, then let's just say this vector v needs to be mapped to another vector v, but 0 has to be fixed. Right, so you can kind of see how this vector needs to be kind of rotated. Right, so O2 is kind of a set of rotations and reflections that fix 0. And it turns out that every finite subgroup, this should say finite, every finite subgroup of O2 is isomorphic to either the group of rotational symmetries of an n-gon, which is the cyclic group Cn, right? Because if you think about an n-gon, I should take a square. Then what are the rotational symmetries? Well, you can rotate it by like this. You can map this edge to that one, or you can map this edge to that one, or you can map this edge to that one, but then you're back to where you started. This is kind of the cyclic group C4. And or it could be the dihedral group, which James has already talked about. So every subgroup of O2 that is finite is one of these forms. Cool. So we'll skip through this example, but basically that's the group O2. Cool. So you can actually read that over in the lecture slides afterwards, but we'll move on to SO2. So SON is an infinite subgroup of the orthogonal group ON. And it's called the special orthogonal group. And basically it's a group of all orthogonal matrices with determinant 1. So you might remember that an orthogonal matrix can have determinant 1 or determinant -1. What we're basically doing over here is we're taking this and we're saying we'll just take these options. So SON is equal to the set with determinant equal to 1. And by extension, SO3, that's a special orthogonal group of dimension 3, and it can be described as a group of rotations in R3. So we can also have reflections for isometries, but what we're basically saying for SO3 is remove reflections, and we'll just leave ourselves with rotations. And much like what we did with O2, every subgroup of SO3 must be one of the following. So it could be the cyclic group Cn. We can still have that option. We can have the dihedral group Dn. And something to note with the dihedral group, right, in SO3, let's just say we have a nice plane here. And we'll take the square example from before. So James would have showed us that the dihedral group is the group of symmetries of this square, and it consists of rotations and reflections. But in this case, we can't actually have reflections, right? So we can simply have rotations by rotating this edge around, so these vertices from there to there. But what would a reflection actually be? It's actually going to be a rotation of this entire plane up and down like that. So if you imagine this like piece of paper lying on the floor, you basically take it and you move it and you tilt it, and then you basically flip it over. It's like taking this paper and flipping it over until you get the same square, but upside down. That's what the rotation flipping the plane means. Right, we can't actually have reflections. It's going to be a rotation that flips the plane upside down. And the third type of finite subgroups of SO3 is the group of rotational symmetries of a Platonic solid. And there are only 3 of these because we have 5 Platonic solids, but the rotational symmetries of the cube and the octahedron are the same. And the rotational symmetries of the icosahedron and the dodecahedron, they're also the same. So there are 3 subgroups here. How do we actually classify those rotational symmetries of the Platonic solids? Well, there's one theorem that we should know, which is that the rotational symmetry group of a Platonic solid has size equal to the number of faces times the number of edges on each face. Because if we want to rotate this in such a way that it's still the same solid, then we'll take this, basically face, and we can move this face anywhere else. So it could move over here. How many options do we have for that? Well, it's number of faces. Next thing we want to do is we can also rotate these individual faces, right? And if you want to rotate a triangle, well, there are 3 edges. So this edge can go over there, or it can go over there. And so the number of options for that is the number of edges. So for the octahedron, for example, it's 8 times 3 equals 24. And how do you actually classify each of those symmetries? Well, there actually is a simple way to do it, which I'm sure we've gone over before, for example, in the assignment for this course. But what you can basically do is you can break them down into 4 different subsets. So there's the identity transformation, which is just nothing. That one's just one transformation. Or you can rotate about an axis joining the midpoint of opposite faces. So for example, over here, opposite faces, you can basically rotate this. You can rotate this square around. So imagine this cube basically rotating around by 90 degrees. The second type, or that's this type over here. The second type is rotations joining opposite vertices. So let's just take this for example. We're basically rotating it around this axis. In this case, let's actually just zoom in a bit. If we imagine this cube kind of tilting around, then there are actually 3 edges surrounding this vertex, and each of these edges can go to 3 places, right? So this would be a 120 degree rotation, and then you can do another 120 degree rotation. But basically, each of these edges can go to 3 different places, right? So that's this one over here. And finally, you can do axis joining the midpoints of opposite edges. So imagine this one. We've got the cube, we've taken the opposite edges, and we've got this axis. Well, you can rotate it completely around here. But what you'll notice is that there's just one edge here. So to actually get a proper rotation that preserves the cube, you need to rotate 180 degrees. And there's a proper way to classify it. So you can actually break down, remember the cube has how many rotational symmetries? Well, it's the number of faces, which is 6, times the number of edges on each face, which is 4. And that gives us 24. Right, so for this example, right, we've got the identity transformation, it makes up one of them, and somehow we need to get through the other 3 of them. We need to get to 24 in total. So in this example, we'll take the ones joining opposite edges. So what you have to do to find out how many of these there are is you have to find out, number one, how many pairs of opposite edges are there. Well, let's think about that, right? How many edges are there in total? Well, that's just going to be 12. Divide that by 2, that's the number of pairs, we've got 6. And for each of these pairs of opposite edges, well, there's actually only one rotation we can do. Because, think about it, there's only the 180 degree rotation, and you'll get 6 times 1. Then we look at the rotations about an axis joining opposite vertices. That's going to be rotations about this axis. Right, and so what you can think about is that, number one, how many pairs of opposite vertices are there? Right, and what's that going to be? Well, that's going to be the number of vertices, which is 8, divided by 2, which is 4. And then we think about this, right? There are, again, 3 vertices. So each of these vertices can go to 2 other places. We're not considering the case where the vertex just stays by itself, because that's the identity. But this can go over here, or this edge can go down there. So there are 2 options. The 2 comes from the number of edges in total, minus 1. Cool. And the last one over here is we're looking at the rotations joining the midpoints of opposite faces. So first of all, how many pairs of opposite faces? Well, 6 faces, so we got 3. And the next thing we're thinking about is, well, how many ways can we rotate this? Well, each of these vertices can go to 3 other places. A can go to B, it can go to C, or it can go to D. Right, and this would correspond to number 1, a 90-degree rotation, a 90-degree rotation, or the last one overall is a 180-degree rotation. Cool. So those are our 3 options. Okay. That's where we get 3 times 3. We'll move on to G-sets and group actions, which is actually what we're going to focus on. And we won't take too much longer, but we can start to think about a group acting on elements in a given set. And the way we do this is by defining a map such that G acts on that set. So a map from G times S to S. And basically what we do is we write G dot S, where S is an element of the set, this is an element of the group, is equal to some element of that set. Right. So basically we say that it acts on the set as long as this condition holds. So this is associativity. GH acting on S is the same as H acting on S and then G acting on that result. The next thing is that the identity when acting on S needs to just form S. And once we've got that set and that operation defined, we've basically got a G set. Yeah, so we'll skip over this, but basically that's what a G set is. A G-stable subset, a subset T, an element of S, is called G-stable if when you take G to, okay, so what is this? G dot T. We've seen like GT before, that's all the options you can get from multiplying elements of G and T together. Well, what G dot T would be is all the possible elements you can get from having an element of G act on an element of T. Right, so what this is saying is that if you take all the elements of G and you make them act on T, you don't get any new elements. It's still a subset of T. So another way this is commonly written is G dot T is an element of T for all G in the group and T in the subset. Basically, we're saying we don't get any new elements from doing the action on this set. And what about orbits? So the orbit of S is written like this as well. So you can see this notation again. This is basically the subset that is given by G, all the elements of G, sorry, I'll write this again, all the elements of G acting on S, right? So it can be thought of as all the elements of S that you can get to from acting on this single element S, right? So it's also the smallest G-stable subset of S that contains S, because basically you're taking S and you're saying, what are all the elements of S I can get to from acting on it? So, slides is with this theorem on orbit structures. So if you define a relation as S is equivalent to S prime, if and only if S is in the G is in the orbit of S prime, then this is an equivalence relation. And what that means is that the G orbits of a set partition a set into disjoint subsets. So you take all the orbits that you can possibly get in a set, and they all sum up to create the set. G1, G2, G1 inverse. Then the orbits of G are called conjugacy classes. We'll skip through this because we don't have much time. But now we're looking at G-set morphisms. So going back to what I did before, I'll just go over it just because of the technical difficulties. The G-set morphisms, what we've got basically is that you have a morphism between two G-sets, and you need this condition that phi of G dot S is equal to taking G out. So you can take G out of the morphism, is equal to G dot phi of S. And if that's true, then basically phi is called compatible with the group action, or G equivariant. And so if phi is also bijective, then the G-sets are called isomorphic. And we write it very much the same way. I'll rewrite this. S1 is isomorphic to S2. Cool. With stabilizers, we've got stabilizers of the element S in S, and that's actually the subgroup of G, right? And it's a subgroup of G such that G dot S is equal to S, which basically means it's a subgroup of all elements G that fix this element, right? So that's a stabilizer of G. And there's this theorem that basically, if you consider the orbit and the stabilizer, the orbit is isomorphic to the quotient of G by the stabilizer. And if you convert that to an order equation, it means that the size of the orbit is equal to the order of the group divided by the size of the stabilizer. So in other words, the size of the stabilizer times the size of the orbit is equal to the order of the group. Right, so thinking about that as a whole, it means that what is a stabilizer? The stabilizer is the set of all elements in G that fix S. So if the stabilizer is really big, then a bunch of elements in G all map S to itself, which means that the orbit is going to be pretty small, right? Because you can't get to many other elements of this group. You can't get to many other elements of this set by acting on an element, right? So the bigger the stabilizer, the smaller the orbit. And that's why we have this equation. Intuitively, that's why the size of the stabilizer is inversely proportional to the size of the orbit. And we got to this example with the orbit stabilizer theorem. And I'll go through it again just because the slides were frozen. But what we'll basically do is think about a certain group, so H times K, acting on HK according to this map. Right, and basically we want to use the orbit stabilizer theorem to show this particular identity. So clearly we want to be using that second corollary. So the size of the orbit times the size of the stabilizer equals the size of the group. Right, and to do this we need to know that G is equal to H times K and S is equal to HK. And now we want to use this and apply it to a certain element S. And a really nice element to use is the identity element. So S equals 1G. Right, so if we take S equals 1G, then we can think about this theorem. In terms of 1. So then we have to calculate the orbit of 1 and the stabilizer of 1. So think about the stabilizer of 1. It's the set, basically you sub it in, the set of all elements in H times K such that H1 times 1 times K1 inverse is equal to 1 itself. Right, so rewriting that, we've got h1 k1 inverse is equal to 1g. Okay, so that's a good start, but this is actually equal to h1 is equal to k1, which means that these two things have to be the same. When is that possible? Remember, this is in h times k. This has to be in h, this has to be in k. So if they're the same thing, they have to both be in h and k. So we can rewrite it as this. It's a set h1, h1 in h times k, such that h1 is in the intersection of the two sets. Right? And what will the size of that be? It's just going to be size h and k. Now we're doing the orbit. So go back to the definition again. The orbit is just a set of all elements that you can get from acting on 1. So h1, k1 inverse, right? Because this thing in the middle is just 1. So it's a set of all h1 times k1 inverse for h1 in h and k1 in k. And that's just the set hk. Because we know that basically what we're doing is we're taking any element h1, we're multiplying it by an element in k, and so that has to be hk. So moving back to our equation, we know that the size of the orbit, so what was the size of the orbit again? It was h, okay? Needs to be equal to the size of the total set, so total group, divided by the size of the stabilizer, so h and k. Right, and that's going to be equal to also h times k on h into k. And the reason for that is because this is just the external direct product, so you can write it just like this. Cool. And that's what we get from there. This is an example of stabilizers, which we will skip just because of time, but you can get some interesting questions from that. We'll finish off by counting orbits. So we need to understand first of all the fixed point set. So given a certain subgroup of G or a subset of G, it doesn't need to be a subgroup, the fixed point set of this subgroup is equal to the set of all elements in the G set, such that h.s is equal to s. Right, so the set of all points that are fixed by h. It's different from a stabilizer, because a stabilizer is a set of all elements that fix a given element s. But the fixed point set is equal to the set of all elements that are fixed by h. Right, and so what you can do is you can also count the number of orbits. So you can use these fixed point sets to count orbits. So the number of orbits is given by this formula, 1 divided by the order of G times summing up over all the elements of G, the sizes of the fixed point sets. Right, so what we can do is we can use this example in a certain question. So we've got G, a finite group, acting transitively, and transitively means that there's only one orbit, so S on G is equal to 1. And it's acting on a finite set with more than one element. And we want to show that there's an element with without fixed points. Right, so basically a good equation to use would be this equation we just got. Right, and the reason why is because we're trying to find fixed points, and we're trying to deal with transitive sets. So sets such that this size is actually equal to 1. So we'll start off with this equation. So 1 is equal to 1 on the order of G times the sum over all elements of G of the fixed point sets. So we might want to try to do this by contradiction, right? Because we want to show that there's some kind of reason why at least one of these has to be equal to 0. So maybe we'll say that this is actually greater than 1 or equal to 1 for all elements G. And so what we'll work out is that over all of these elements, so the G elements, we've got 1 plus 1 plus 1 plus 1. And what we'll work out is that there's a very special element. So for example, maybe we can try the identity element. So what's the fixed point set of the identity element? Well, by definition, that's the set of all elements that are fixed by the identity element. And because the identity element fixes everything, this is actually the entire set. So at least one of these elements, G, needs to get you a fixed point set that is equal to the size of the entire set. So in a way, right, we've got this sum is actually greater than or equal to 1 plus 1 plus 1 all the way down to the size of the set for this identity element. So what we've written down is we know that for the identity element, s to the power of 1g is equal to the entire set. And we know that there's more than one element, so this thing over here needs to be greater than 1. Right? And so it turns out that this has to be greater than the size of g. Right? Because over all of these elements of g, we've got 1 plus 1 plus 1, all the way down to this one, which has to be more than 1. So all together, it's greater than g. And that means that this equation is greater than 1. But that's a contradiction, right? Because we know it acts transitively, which means it has only one orbit. Cool. All right, so it follows then that at least one element, G, in this group G, must not have fixed points. Cool. And what we'll do is we'll finish off there. There's this lovely final question that you can look at, but it's quite similar to number 1, the assignment, and it just generally uses counting orbits in general. But we will finish off the seminar there. So thank you all for coming. Sorry about the technical difficulties from before. When we do upload the recording, we will make sure that the part with the slides not showing up, we'll just cut that out. So yeah, thank you all for coming. Hope you enjoyed that seminar, and we'll make sure to see you back on Thursday if you can make it for the second part of the seminar, which is on rings and fields, from 2 p.m. to 4 p.m. Right, so thanks everyone, and have a great time studying, and good luck for your finals. No worries. Have a good one.